Oh, hello, Dylan. Sorry if you tried to talk to me, I didn't hear you. Are you there? Dylan, you're muted if you're talking. I can't hear you. You gotta unmute yourself. Oh, there we go. You there? Hello, Dylan.
What's up? Computer issues were.
Oh, there we go. There we go. Good stuff.
All right, sweet.
You're the first person in, so we're just gonna wait a few minutes, see if some other people log on, and then we'll get started, okay?
All right.
Dylan, if you want, make sure you do have up the Google Classroom because we're gonna be grabbing a couple things from there.
All right, I got Google Classroom already pulled up.
Nice.
Well, I need like well, this is my first Zoom meeting, so I don't really know what
Yeah, you're good.
work goes on.
We're gonna go over the lecture. You can either type in the blanks as we go through, or if you just want to like take a sheet of paper and send me a picture, that's fine. Whatever works best for you. And then for the articles and stuff, you're gonna download it, answer the questions, and then send it back to me. And that's really all we're doing today. Not too terribly much.
That don't sound too horrible.
Another one. Hello, Mindy. Mindy, is your last name Ellison? You're muted if you're talking, by the way.
Yeah, see, that was my problem. I was muted and my computer wasn't giving me any audio, so I didn't hear anything.
Hi, Mindy. You're
Hi.
muted. Did you hear me? Is your last name Ellison?
Yes.
Okay, thank you. Go ahead and grab open your Google Classroom because we're going to be working out of a couple things out of there. And we're just waiting for a few more people and we'll get started here in 2 or 3 minutes. All right, guys, we're going to go ahead and get started. And then if people pop in later, they can just fill in as needed. So yesterday we talked about a whole lot of stuff, including the Big Bang, including taking a look at gravity. And what we're going to do now is we're going to take a look at what started to form about 300,000 years after the Big Bang. Our focus is going to shift to focus on stars. We get a lot of information from stars. So two things we're going to be taking a look at today. First, we're going to take a look at how we analyze the information from stars that we get. And the second thing we're going to be doing is we're going to be looking at how stars change over their lifetime. Okay. So if you guys would, go ahead and make sure you have open the guided notes. Those are the fill in the blank ones. As I pull up today's PowerPoint. So, okay, let me here, I can share so you guys can see. Share screen 2. All right, so I closed it. In Google Classroom. Earth and space. So you got classwork, we're in day 3, and it's the spectral analysis one right here. Everyone can see it, yeah?
Okay.
Okay, you can just click on that to open it up, and it should look like this. And if you guys want, you can just type. It makes a copy for you and saves on your drive. So this is here for you. But this is what we're going to be going through for the notes. Okay. All right. Okay, so the first question that we have to ask ourselves is, how do we really know what's out there? Does anyone know what the furthest away from the planet humans have actually been?
The moon.
We've been to the moon, yes. And we've sent some satellites and stuff to the different planets. We've gotten some rovers to Mars, and that's about it. So really, like, mostly our closest neighbors and nothing outside of our solar system. We actually do have one very old satellite that's kind of hurtling out towards the edges of our solar system. But because it's so far away and it takes so long to travel, that thing is quite old. So we're not going to get the kind of data that we would expect, in today's day and age to get from it. So the question is, space is huge and we've never been farther than the moon. How do we know what things like stars are made of? How do we know what distant galaxies have in them? And the key comes down to what information do we get from them? So what do you guys think? How do we explore outer space?
Telescopes.
Exactly, we use telescopes, okay? There are many different types of telescopes that we talked about yesterday. But one of the main types of telescopes uses light, okay? Let me go ahead. I am gonna mute you guys. So if you need to say something, just go ahead and unmute as needed, okay? That way phones go off or something. It's not a distraction. But moving forward, so what we're gonna focus on is light, because light is a really, really interesting thing that tells us a whole lot more about the object than you initially think, okay? So let's go ahead and talk about what is light. Well, light, the light that we see, is a very small fraction of this much bigger scale. So this whole scale right here, okay, you guys can see my little red highlighter thing, yeah? This whole scale here is called the electromagnetic spectrum, okay? Basically, it is a way to categorize waves, okay? Because light is nothing but a wave. And it goes from very, very long waves, like AM radio, to incredibly short waves, like the gamma rays, okay? So if we look at this list, there may be some things that we can kind of recognize here. We've got radio, we've got AM radio is the longest. That's why AM stations can send out signals over the furthest area. because their waves are really big, so they can travel long distances. Here we have TV waves, FM waves, so radio and TV is in the bigger end. So this is 1 meter, so that meter stick we were looking at yesterday, that's about the size of one wave of a, why won't it let me do that? Huh. In any case, it's not letting me write on the PowerPoint like I would like to. Oh, goody, now my thing's going on. So anyway, basically what this looks like, I'm gonna have to do it with the laser pointer, but a wave is just something that goes up and down and up and down. And this is how light travels up and down. And how wide the wave is what we're talking about, the wavelength. So if the crest is here and it takes this whole screen to do one complete wave, that's a really big wave. So that's like these over here. And then if we go like up and down and up and down and up and down and up and down and up and down, those are the smaller waves, like over here. So just beyond what we can see on the bigger side is called infrared. Does anyone know where infrared rays come from? So if you have, I know I'm making myself really old. Has anyone ever seen the movie Predator? You know, that little,
Yes.
that hunts, you know, when it goes into the predator, like you can see through their eyes and the things that are giving off heat glow, they're like reddish and it's kind of like a bluish color. That is infrared light. So anything that gives off heat is glowing with infrared light. So right now, our bodies are actually glowing. We can't see it because our eyes are not able to detect that kind of light. It's too long of a wavelength. But what's really interesting is that all of us are glowing right now. Anything that is giving off heat is actually glowing with infrared light. Then this little narrow path right here, right where I have the laser pointer, that is everything that our eyes can pick up. Okay, so we can really only see a tiny bit of the electromagnetic spectrum. It's much, much larger. Even though we can see all the colors in the rainbow, our eyes are actually pretty well, evolved for our species, so to speak. We're not, we're not direct hunters or things like that, so we don't have eyes like a hawk or something that can just zoom in super far away or whatnot. But we can see lots of colors and we have pretty good motion. We see movement pretty well with the edges of our eyes. We can see detail really well with the center of our eyes. So we can see a good amount. But on this grand spectrum of things, it's really a small amount that we can see. On the shorter end, just beyond what we can see, we get to things like ultraviolet rays. Has everyone ever heard of UV light or know where UV light comes from? What gives off UV light?
I know what a UV light is, but not.
Yeah.
Yes, yeah.
So UV light, again, it just is putting out, in addition to what we may be able to say, it's also giving out smaller waves that we can't see. Ultraviolet light is why we need to wear sunscreen. So like UV lamps can be used in like tanning beds and things like that, but mostly ultraviolet light comes from the sun. Okay, and what can happen is this ultraviolet light this is the higher energy side. This is the lower energy side. So this actually has enough energy that it damages our DNA, which is, or it can damage our DNA if it makes contact with it, which is why we have to wear sunscreen when we go outside. Birds and insects use ultraviolet light a lot. We have patterns on our skin that we can't see. Plants have all kinds of beautiful patterns that we can't see because we can't see the reflected UV light. But there's a whole world of glowing patterns and stuff like that on stuff that we don't see because we don't see ultraviolet light. If you go higher up on the energy, we get to things like X-rays. The X-rays can travel through your skin, no problem, but they stop when they hit bones, which is why, when you break a bone, you get an X-ray. You put your arm or leg or whatever over the photograph, and what happens is it exposes that part of your body to X-rays. The X-rays pass through your skin and hit the film on the bottom, making it dark. And they get absorbed by the bones, which makes the bones appear white on the film. And then you can see if there's any breaks in the bones or things like that. And then the highest energy level are gamma rays. And this is also given off by things like the sun. Very, very, very high energy, very damaging radiation and stuff like that you don't want to get too much of. okay? But let's focus for now just on this tiny little section right here, what we call visible light, okay? So the part of the spectrum that we can see, we call visible light, and we see different wavelengths as different colors, okay? The reason you see color, it's all the same energy, but the reason you see color, it has to do with the size of the wave, okay? So if we start out here on the smaller end, the higher energy level, smaller wavelength end, we have purple or violet. Remember, what was just beyond purple was ultraviolet light, UV light, ultra, beyond what we can see in the purple end, okay? Too high of an energy. So we go violet, then we have the blues, the greens, the yellows, the oranges, and then we get into the red. Remember, what was on the other side of the red that we can't see is the infrared. That's the light given off by heat. So it's very well named to see, you know, for the light that we can't see on either end. We have infrared beyond what we can see on the high end, and we have ultraviolet, which we can't see on the small end. So it's really interesting when you're looking at something, the light reflects off of it, and the wavelengths that come off of it determine what colors you see. It can be more than one, okay, which will create a combination of colors, or, you know, the colors will mix and it'll appear, you know, like brown or a different color that we can't see. So it all has to do with wavelength. Higher the energy, longer the wave, lower the energy. Now, white light is not actually white. Okay, when we look up in the sky and we see the sun, the sunlight appears to be like a whitish color. What you can do to that color, and the reason that you're seeing that is because you're seeing all the colors expressed at once. So when all the colors are expressed, you get a white light. And what you can do is you can send that light through a prism. So here's the light coming through. The prism is just a triangular piece of glass, okay? This also happens sometimes when it rains. We'll talk about that in a second. But the light, as it travels through this glass, it gets spread out. And when it spreads out, you can start to see the colors by the different wavelengths. So it actually takes the light, spreads it out so you can see the smaller end, the violets and blues, and the larger end, the oranges and the reds, the full rainbow. So what happens when it's raining? What sometimes do we see if the sun is shining and it's raining? Sometimes we look up in the sky and we see
Rainbow.
a rainbow, absolutely. And what's happening at with the rainbow is the sunlight's coming down, it's hitting the water, and the water is acting like the prism, causing the color and the light to spread out. And that's why we end up seeing the rainbow. Now, why do we care about this? Well, because what is the only piece of evidence that we get? What's the only information that we get from distant stars? What's the
Light.
We get their starlight. You look up in the night sky and you see hundreds and thousands and millions of stars. And guess what? There are millions and billions and trillions more that we can't see because they're too faint. But the key here is that their light, remember, travels in a very predictable way outward. It travels from that star, however many light years, hundreds, thousands, millions of light years away, travels for an incredibly long time at an incredibly fast speed, and eventually hits here at Earth. And what we do, or what scientists do, is we use an instrument called a spectroscope. A spectroscope is basically a telescope that takes the light that it gets, sends it through the prism. Okay, so it's going to do exactly what this slide is showing you. The light comes in from the star, it sends it through a prism, and it causes that light to spread out. So why is that important? Well, what we do is we look for specific patterns of wavelengths, certain colors. What's really interesting is when you heat things, they start to glow. They give off light. Light is one of the forms of energy that things give off when they're heated. What's really, really cool is that when any element is heated, it begins to emit light. And each element has a unique pattern of lights that it gives off. So for example, what we have here is, I don't know if you guys can see this on your screen. We've got one in the purple, one in the dark blue, one in the light blue, and one in the red. And what we can do is we can take light, look for what colors or what wavelengths it's giving off. And each set of wavelengths is like a fingerprint. My fingerprints are different than your fingerprints, are different than your sister's, your mom's, your dad's. Everyone has a unique fingerprint. Well, all elements have a unique fingerprint of light that they give off when they glow. So for example, the one that we're looking at right now, this is hydrogen. So hydrogen has that purple, that blue, dark blue, that light blue, and that red. Anytime we see this pattern of light show up, it tells us that that star contains hydrogen. And should stars contain hydrogen? Absolutely. There are very, very few stars that have no hydrogen in them. And this is because, remember, the two elements made by the Big Bang, 75% of the universe was hydrogen. Hydrogen is literally everywhere. There's nowhere that we can look that we don't see the signature of hydrogen. We don't see this pattern of light. So we know hydrogen is found all throughout the universe. And that, again, strengthens our understanding that hydrogen was the predominant element after the Big Bang. So whenever we see this specific pattern, and not just this pattern, there may be thousands of lines in here, but when we see these specific 4 bands of light, we know that that star is containing hydrogen. And what this is called an emission spectrum. Emission means that it's giving it off, okay? Emission spectrum. Dylan, were you able to get to the notes? I'm sorry, I just saw the email that you requested access not in your school account. Or you are your school account. Why is it?
Yeah, it's making me like request to put any of this stuff in there.
Mine won't let me put anything on it.
I know what I did. I goofed. Let me fix that. You guys let me just get going. You shouldn't be like, hey, stop.
Honestly, I thought it was like part of it because I saw the PowerPoint was there too. So I was like, okay, I'll just go back and
I'm sorry.
Like we'll listen for the lecture right now, and then we'll do that.
That's what I was gonna do too.
Sorry, guys. So there's a little box that I have to check, and if I don't check it, I thought these downloaded. Maybe these don't. That's the slides. Oh, I don't want this to do it that way. Okay. Yeah, for right now, I guess just listen along. I'm sorry. I don't know what I'm doing wrong to not make this work, but it's not working. So, all right, moving on. Just listen to this. And like I said, we'll go back and fill in things as we need to. Pull the PowerPoint back up. And all right, now there are 2 different types of spectra that we can analyze. One is an emission and one is absorption. So there are certain things that, there are certain colors that elements give off when they're heated, that's the emission. And then there's certain bands of light that things absorb, and that's the absorption spectrum. So basically light's passing through there, what does it keep in, what does it hold? Both work equally well, but we're only gonna focus on the top one, the emission spectrum. Okay, this one right here. So by using a spectroscope, scientists can analyze all the wavelengths that are emitted by a star, and that allows them to tell exactly what the star is made of, even though it might be thousands of light years away. Every single element gives off a unique pattern. But the key is that hydrogen is going to give off the same pattern no matter where it is. This example of calcium is going to give off the same bands of light no matter where we find it. This is uranium, this is oxygen. You can see that they may have some that line up, but the key here is that this unique set is oxygen, this unique set is uranium. So we're looking for complete sets, not just certain things that match up. All the lines have to match up in order for you to tell that that star contains that element. All right, so already we can tell exactly what a star is made of without having to visit the star, just by looking at the light. But guess what? Light contains more information than just what elements that star has. This is really cool. So remember, and I know I keep going back, but this is related to the Big Bang. What we are talking about, the 2 pieces of evidence that we have for the Big Bang, the major ones, are the background radiation. Remember that leftover radiation we found deep in outer space? And the other thing that I said is we needed to show or prove a way that the universe was still expanding. And this is where light can really help us, okay? When an object, such as a star or galaxy, is moving towards us, the wavelengths that are given off by it get crunched together. So instead of being nice and spread out at their normal space, they actually get a little bit more narrow. And remember, well, if we go all the way back real quick, okay? If we go back here, the shorter end is this blue or purple color. The larger end is this reddish orange color. So what happens is as the light is traveling, if the object is moving towards us, things get compressed. So if it were normally like about 600 meters, now it's about 550 meters. There's a shift, right? There's a shift, things get smaller. And what we call this is we call it a blue shift. So if we ever look at a star's light and all of the lines are there, but they look a little bit shifted towards the blue end, we know that object is moving towards us, and we call it blue shift. Now, what if an object is moving away from us? Well, if it's moving away from us, those wavelengths get a little bit stretched. So they get a little bit larger, which actually pushes the colors down towards the red end of the spectrum, the lower frequency, okay? And we call this a red shift. So what we do is we look at the light of all the incoming stars and we see, are we seeing a red shift or are we seeing a blue shift? Because that not only tells us what elements it contains, right? We can analyze the light to see that, but depending on how it's shifted, that tells us what direction it's moving. So light not only tells us what it's made of, but it also tells us what direction that object is moving, which is kind of crazy. This phenomenon is called the Doppler effect, okay? The Doppler effect is not unique to light. It can happen with anything with a wave. And I don't know if you guys know this, but sound is also an example of a wave. If you ever see those little like, equalizers or things like that, or the little, microphone lines, that is just a wave of the sounds. And what happens is when an object is coming towards you, the sound gets crunched again, right? And the pitch sounds a little bit higher. When an object is moving away from you, the wavelengths get stretched out a little bit and the pitch gets a little bit lower. If you've ever been on the sidewalk as a car or an ambulance or a fire truck goes by, you've heard this, okay? Or a cop car. As that siren of that fire truck or whatever is coming towards you, the siren sounds to get higher and higher and higher in pitch. And then as it passes you and goes away from you, then it starts to get lower and lower and lower in pitch. Now, I don't know if you guys are gonna be able to hear this sound, but hopefully you can. And I'll play it more than once, but I'm gonna play a sound of a car that's coming towards us and then going away from us, okay? So listen to here, you can hear the pitch. Okay, hopefully that wasn't as loud for you as it was for me, but you heard as that car came towards us, it went, that pitch went up because the sound was being compressed. And as it went away from us, the sound became stretched and it pitched lower. Okay, I'm gonna do it one more time. Okay, so we can hear again, it goes up in pitch as it comes towards us, goes down in pitch as it goes away from us. So again, if the frequency is shifted towards the red end, it means it's moving away. If the light is shifted towards the blue end, it means it's moving closer. Now, here's the other crazy thing. Guys, the amount of shift, how far it is moved one way or the other, also tells us the speed the object is traveling. So light, something as simple as light, not only tells us what it's made of, it tells us which direction it's moving, but light can also tell us how fast the object is actually moving. Okay, so the greater the shift, the greater the speed. Okay, so how do we use this in astronomy? Well, here's the wavelengths emitted by helium. Okay, and it's going to be a little hard to see, but this is the pattern of wavelengths that we see from helium in an actual star. So the top one is if we heat helium in a lab, this is what we see here on Earth. Heat up helium, you see red line, yellow line, couple green lines, couple blue lines, couple purple lines, right? Now, if we look at the second one, this is what we see when we actually analyze a star. It still has the red one, it still has the yellow one, it still has all the green ones and the blue ones and the purple ones. But if you look very closely, and this is where it would be better if you actually had the notes up, and I apologize, I'll figure out how I can fix that. But if you look on this, what you see is you see that this yellow line, this is the easiest one to see. If I come straight down from this yellow line, do you see how I'm actually a little bit to the left of where this one, where the second line is? It's been shifted what way? It's been shifted towards the red end. Same thing I can do with this red line. If I bring this little power or this little mark, we can see that it doesn't quite line up. It has been shifted to the right. So what does that mean about that star? Who can tell me? If it's shifted towards the red end, what is that star doing?
Moving away.
It's moving away from us, okay? So first we can tell it means it has helium, right? Because it has all these lines, it has helium. Second, that it's moving away from us. It's experiencing red shift, okay? And again, the greater the shift, the faster it's moving, okay? So if I take, this is the helium that we see here on Earth. If I bring this line down, we can see that second one is shifted a little bit. If I keep bringing it down pretty straight, we can see how much of a gap there is between the first and the third one. So that means this bottom one is moving much faster than this middle one, because this middle one shifted a little. You can also do it with the yellow, right? Bring this line down and boom, you can see how big that shift really is, okay? So we can tell what it's made of, which direction it's moving, and how fast. So here's the rub. All of the light from every single star, from every single galaxy, and I'm talking every single one that reaches the Earth is red shifted. So the light from the nearest star to the furthest star, it's all red shifted. So what does that mean everything is doing?
Moving.
Moving, yes, which way? Towards or away?
Away.
So everything is moving away from us, okay? So here is a question. How can every single thing be getting further away from us?
Strong gravity pulling it away.
Maybe. There could be some strong gravitational forces that we're not aware of outside, but what else might be the reason that things are getting further away? What was the universe constantly doing?
Oh yeah, expanding.
Expanding, exactly. And this is honestly our strongest piece of evidence for the Big Bang. The fact that things are still expanding, okay? The only possible explanation is the universe is expanding. And if the universe is expanding, it must have been much smaller. All right, we work it back. And that's another way that we play it back. We look at the rate of expansion, we play that backwards, kind of like we did with that little video of the exploding watermelon in the notes from yesterday. And we can see that this expansion from one single point, okay? And that is really key. Every single star, every single galaxy is still expanding. It's still getting further away. And that's really, really key to our understanding of the Big Bang. Okay. All right. So that's it for the notes for today. Let me pull up the classroom again. I'm going to work on figuring out how I can get this so that it doesn't just open and you can work on it. But what I would like you guys to do now is there's two other things you guys can work on. I'll put them at the top of the day. We have the stars, life cycle of stars, which is a little reading. And then we have the stars exit ticket. And this one should work just fine if you click on it, okay, hopefully. I think this one will actually make a copy for everyone. So there's a little reading, there's a diagram, there's ordering for the first one, matching for the second section. It's got some little diagrams that you have to label the steps on. So just match these words down here to what page the star is in. And then there's like a little flow chart and Venn diagram. Do your best on this back one, but we will go over this on Monday just to review back page. But you definitely need to get the first 2 pages done of questions, okay? So just the article reading about the life cycle of stars and then the stars exit, you should be good. Again, just fill it out, send it back to me, and that should work just fine. Okay.
Okay.
That works.
And that'll be it for today from me. I will still keep the Zoom open if you guys need it, just to pop in and ask questions, get clarification or whatever. I will be posting this video up onto the Google Classroom, and I'll provide a YouTube link as well. Yesterday's video is here as well. Maybe it is. Yeah, there it is at the top, the very top. Class videos. So this is the one from yesterday. You guys can just click on this. And I didn't put the link in, but I'll put that now to that other YouTube video. Get a link. Okay. So I'll put that in the description as well. Okay. That way you guys can, if it's easier to do it on YouTube, that's the easier way than do it that way. Okay. So I will be posting this video as well up there once it renders and everything. But if you guys don't have any other questions, just go ahead and get that stuff done when you get a chance. Probably not going to take a look at it till Monday, so you have some time to do it today or tomorrow or whenever. But if you guys don't have any questions, that's all I have. Okay.
Okay.
All right.
All right, guys. Thank you for zooming in, and I will see you on Monday.
See you Monday.
Alrighty.
All right. See you.